Hello, my name is Victor Cola and I'm going to share with you some of the results of our modeling study concerning the probe depth distribution of photon in spatially resolved diffuse reflectance and autofluorescence skin spectroscopy. Optical biopsy refers to spectroimaging techniques developed to characterize biological tissue optical properties in vivo. It differs from conventional biopsy by its non-invasive nature. The data analysis challenge consists in extracting from the measured intensity spectra discriminant information related to the characteristics and concentration of the constitutive elements like absorber, diffuser, and fluorophore. They are valuable information to determine the nature of the tissue. Optical biopsy is involved in the perioperative support of the removal of cutaneous carcinoma. Indeed, its use makes it possible, on the one hand, to improve the efficiency of diagnosis and, on the other hand, to establish surgical margin. Several point spectroscopy techniques have already proved to be effective for cutaneous carcinoma diagnosis. This includes Raman, exogenous and endogenous fluorescence, or diffuse reflectance spectroscopy. In addition, it's also possible to enter several source sensor distances. This is called spatially resolved spectroscopy. It allows to probe different depths. In this context, our lab has designed a spatially resolved device for optical biopsy. This last bears the name of Spectrolive and is used in a clinical study. Diffuse reflectance and autofluorescence spectra are acquired and subsequently exploited to design a real-time device able of establishing surgical margin. If the different spectroscopic modalities are effective in cancer diagnosis, it's because metabolic and morphological modifications due to cancer are responsive for discriminating change in the different output spectra. Here, it's a question to present the main one to which our two modalities, namely autofluorescence and diffuse reflectance, are sensitive, and to indicate in which layer of the skin they appear. Let's begin with the epidermis. The literature reports a decrease in flavin fluorescence between spectra acquired in an healthy area and another in the center of the lesion. Also in the epidermis, a similar behavior is observed with NADH fluorescence. For the papillodermis, this time it's the fluorescence of the elastins that decrease with the growth of the tumor. In the same layer, carcinogenesis is at the origin of the elastosis. That means accumulation of elastotic material and elongation of the fibroblast of the epidermis. Finally, we find in the deep dermis or reticular dermis a decrease in the fluorescence of the collagen caused by enzymatic degradation. The elements introduced so far make it possible to situate the work undertaken. As indicated in a very symbolic way here, it is a question of determining for a couple, wavelengths, source detector distance, if it is sensitive or not to the spectral modification appearing with the carcinoma. In other words, it's a question of providing numerical evidence that a photon at a given wavelength and detected at a given distance is likely to carry the information characteristic of conscious tissue. That is why the result presented here can firstly provide useful tool during the design of an optical multimodal biopsy device, and secondly, it can facilitate the development of analytical photon propagation model that enables inverse estimation of relevant optical properties from in vivo spatially resolved diffuse reflectance and autofluorescence measurements. Let's come to the description of the experience. The first step was to create a digital medium that was as faithful as possible. It was chosen to mimic an healthy ray skin. We turned to a 5-layer model reproducing from the superficial to the deepest layer the stratum corneum, the epidermis, the papillodermis, the reticular dermis, and finally a subcutaneous fat. For the optical behavior, more precisely the absorption, only 5 chromophores were considered, namely blood, water, melanin, lipids, and beta-carotene. The figure on the right shows the contribution of pure chromophore absorption. The final absorption coefficient of a layer is then deduced as a weighted sum of pure absorption coefficients where the weights are the volume fraction of the chromophore in that layer. For the scattering coefficient, this can be divided into a contribution from blood and a bloodless base scattering component. Both are presented on the figure. The contribution of the blood is then multiplied by two factors. The first is the volume fraction of the blood, while the second takes into account the mean blood vessel diameter in the considered layer. By applying the formula described in the previous slides, we finally obtain the absorption and scattering coefficient of each of our 5 layers. The presence of hemoglobin absorption peaks in the irrigated layers can be noted, as well as the diffusion barrier of the stratum corneum. For fluorescence, due to the lack of bibliographical references, simple models of absorption and emission have been constructed using Gaussian curves. Only the main fluorophores were considered, namely keratin, NADH, flavin in epidermis, elastin in the papillodermis, and finally collagen in the reticular dermis. The figure presented offers a summary of the optical fluorophore description with the normalized absorption and emission coefficient spectra. Let me now present our simulation code. It's a GPU Monte Carlo code that we adapted to fit with our Spectralive clinical device. The medium where photons travel is constituted of layers which are described by their thickness, their absorption and scattering coefficient, their refractive index, and their anisotropy factor. The update of photon position in the layer K is done according to this expression, while its new direction is calculated according to NV-Greenstein formula. The absorption is managed by weight loss along the optical path, while diopter management obeys to Snell-Descartes law. Finally, photon death is considered when it escapes from medium or the time of life of rare threshold is reached. To match our clinical device, we had to complete the existing code to integrate the fluorescence modality and add the spatial resolution. Concerning fluorescence, at each diffusion step, one chooses if the photon is purely absorbed, meaning by a chromophore, or absorbed by a fluorophore according to those probabilities. To choose which fluorophore among those present in the layer will fluoresce, a random draw is made where each fluorophore M of the layer carries the expressed probability. A second random draw is then made to choose the emission wavelengths. The emitted fluorescent photon will keep traveling in the tissue by undergoing light-matter interaction according to its new emission wavelengths. Concerning the spatial resolution, photons contribute to the spectrum signal associated to a given distance if it satisfies collection geometry. From the code described so far, tools to characterize the depth behavior of the detected photon have been created. It's the case of trajectory map that, at a given wavelength and at a given source sensor distance, add the final weight of detected photon where scattering events happened. For fluorescence map, it's only the fluorescence event that is localized. Finally, a more quantitative information is obtained thanks to the histogram of probe depth. Now, it's time to share with you the result of the simulation obtained with our realistic 5 layers medium established earlier. Those were acquired with the presented simulation settings. NZ and NR are the number of voxels according to depth and radial distance. The main goal of our simulation is to obtain autofluorescence and diffuse reflectance spectra in the Spectralive configuration. That's why it's presented here, the diffuse reflectance spectra obtained. We can notice the presence of hemoglobin absorption peaks. Here, the autofluorescence spectra are shown at the wavelengths corresponding to the excitation of the Spectralive device. Since the absorption peaks of fluorophore are in the near UV, we notice a decrease of the signal when the excitation wavelength reaches the beginning of the visible spectrum. In addition, the emission peak shifts toward the high wavelengths, which can probably be associated with an increasingly predominant expression of flavin. What information on the path of the photons that contributed to the previous spectra can we have? Qualitative answer can be provided by these trajectory maps. The position of the source is indicated by the red segment in the upper left corner, while the collection fiber is presented by a blue segment. This is a half-section view of the medium, where the black line represents the diopters between the layers. The log has been applied to obtain a nuanced image. We can see that for the more transparent medium on the left and at the wavelengths of 385 nanometers, the photons reaching the detector placed at 1 millimeters from the source penetrate more deeply than for its equivalent at 405 nanometers in the absorption peak of the hemoglobin. For the fluorescence map, we choose here not to compare wavelengths that we fix at 405 nanometers, but rather illustrating the impact of source to detector distances. We can notice the shift toward deeper Z and greater R, and the widening of the probe volume when the distance is increasing. From now on, we bring more quantitative elements with the histogram of maximum probe depths. 3 elements are to be noticed on both figures. The first one is that at a fixed wavelength, the probe depth increases when the source detector distance becomes larger. Secondly, by comparing a wavelength in the near UV, where the medium is optically opaque, and another in the near RR, where the medium is more transparent, we can see that the photon reaches greater depths in the second case. Finally, we note the presence of narrow peaks in the histograms. These are due to the Fresnel reflection at the interface. Processing those histograms for our 4 source detector distance and for all the wavelengths, the maximum characteristic depth probed was calculated by taking the depth average for each histogram. The results obtained are presented through those 4 curves. The horizontal straight lines correspond to the interface between the layers. The fifth one, corresponding to subcutaneous fat, does not appear there. With the available wavelength and distances, we can see that it's possible to probe depths covering the range 100–800 micrometers. Now let us comment more generally on the result obtained. About the medium, we are aware that the proposed simulation does not pretend to characterize any optical biopsy performed anywhere in the body. However, the model followed should guarantee a certain reliability. Concerning the fluorescence, the creation of quantitative tools and the separation of excited fluorophore will be made. Finally, the result obtained for the depth of penetration of the detected photon showed the sensitivity for a chosen wavelength and source detector distance of the diffuse and autofluorescence spectra to morphological change due to carcinogenesis. The logical continuation is then to study how a probe depth contributes to the output spectra. To conclude, we designed a skin-mimicking 5-layer numerical medium that takes into consideration absorption scattering from chromophore and the fluorescence. We adapted the Monte Carlo code in order to fit with our Spatially device, making acquisition of simulated autofluorescence and diffuse reflectance spectra possible. We then took advantage of the power of simulation to obtain numerical information concerning the behavior of photons in depth, this information being inaccessible with the clinical device. Qualitative tools like trajectory map and fluorescence map have been applied, and the exploitation of quantitative histograms allowed to link the wavelength and the source to sensor distance to the probe depth. The presented result can be helpful during the design of an optical multimodal biopsy device and improve photon propagation models that enable inverse estimation from clinical spectra. With that, I would like to thank you for your listening, and I'm looking forward to receive your question.